Okay, now we'll hear from Tom Orlando. Water formation and release via thermal desorption on and within hydroxylated Lunar, Mare, and Highland samples.
Thank you. Sorry about the long title. I am going to switch gears a little bit and cycle back to the very first talk that was given by Brant Jones. This is an overview of some things that were really quite relevant to his model. Brant contributed significantly to this activity, as well as Alex Alexandrov. But I want to point out that it's one that's been ongoing for a number of years with a collaboration, which is quite important, with Carl Hibbets and Darby Dyer. Okay, Brant basically went through this model, but he never gave a real cartoon. So I'm going to give you a cartoon which sort of summarizes most of the relevant information, and then I'm going to point out two specific things in this particular talk, and I'm going to talk about how limited the chemisorption of water is. And the chemisorption is the sticking of molecular water. And then I'm going to also talk a little bit about how you can make molecular water. Boy, this pointer is a real nightmare. Yeah, it does. It locks you in. Like, this is almost written by word, right? It just goes back. No. No. Okay, I'm going to not use the pointer. So the recombinative desorption channel is quite important, and it was really relevant to the model that Brant showed. And what we're talking about is a proton comes in, it hydroxylates, it embeds itself into the regolith, it makes a metal hydroxide, or in some cases maybe a metal hydride. Okay, that's not temperature dependent, but it's dependent upon the flux, obviously. And if the hydrogen isn't captured as one of these stable molecules, it's lost very rapidly as H2, and it desorbs and leaves. And the formation of H2 is via this process called recombinative desorption. Once you form MOH and MH, these don't move very well, so they build up, and in particular, the MOH builds up, giving rise to this 2.8 micron signature. And Brant did a very good job showing how we model its removal, and there's a very weak diurnal dependence, but there's a latitude dependence. And in particular, the latitude dependence we can match very well. The original data, in particular, the data from Tom McCord et al. And the M-Cube folks, with no thermal corrections at all, okay? But in that, we required a step, which was the formation of water by this process called recombinative desorption. And that happens, and I'll show you this, it happens at around 350 Kelvin. So at the high end of where the temperature excursions on the moon go. This heals the defects, and then some H2 can also form. Okay, now we spent a significant amount of time in the earlier days, and this was supported by vortices, producing and basically constructing an instrument to do precisely these types of measurements, and this is what it does. So we do temperature programmed desorption, which is a well-known technique in surface science, but the surface scientists tend to look at nice single crystals. And so we've done something different here. We wanted to do minerals and powders and regolith samples. So we built this, and we have an important thing where we can heat the substrate at a very known, well-controlled rate, measure the release of the adsorbate as a function of the substrate temperature, and we're measuring that with a quadruple mass spectrometer, so we know the mass. So we track the removal rate on a mass resolved basis as a function of the temperature, and from that we can extract out an important quantity, which is called the binding energy. This is all done under ultra-high vacuum, which is 2 times 10 to the minus 10 torr. We spend time getting to that vacuum because at 1 times 10 to the minus 6 torr, you have what is called a Langmuir. And you'll see several of these plots with Langmuirs. 10 to the minus 6 torr is 1 Langmuir. 1 Langmuir is 1 layer of molecules per second hitting your surface. You don't want that, so we are at 10 to the minus 10 torr, so we have 10 to the 4 seconds to make sure that that's really clean. So what's on the surface is what we put on the surface, and that's an important point. And then we do this, we do controlled dosing, and we have a novel thing here, which is this cooling stage. You know, if it's cold, things go in, and 10 to the minus 6, at less than 180 Kelvin, you'll conform to ice. 100 Kelvin, things hit and stick, and you get a lower and lower in temperature, and they stick, and they make ices. What is a problem here is if everything's cold, everything sticks, and everything gets stuck, and has an adsorbate on it. So we've controlled this so that we can remove this and do a measurement where there's no background, okay? Now, I want to give you an overview of how you do a standard TPD analysis, okay? And Brant mentioned this. So the standard way of doing an analysis of a TPD spectra, where you're measuring the release rate of water or an adsorbate as a function of substrate temperature, it's over here. Okay, this is the water coming off, and then you're varying the temperature across this axis here. You can see that there's 3 peaks here, and there's a whole bunch of lines here. These bunch of lines are related to the coverage. So at low coverage, I have only this low one coming off here, and you can see it builds up and the peak shifts as it goes over, as I go to higher coverage. This peak just goes straight up, and this peak sort of shifts a little bit. So these are mapping out different types of adsorbates. Okay, so this is sort of a adsorbate, so it's water just sticking, this is ice. Okay, this second peak here, that's chemisorbed water. That's water in the molecular adsorbed state as water molecules. And over here, this is broken up water molecules. It's water that sort of hit the surface and broke up, and it's coming off as water because these OH groups are recombining and forming water. Okay, so there's a very simple approach to analyze this with the Polanyi-Wigner equation where theta is the coverage, delta E is the desorption energy, that's what we're after, temperature at time t, n is the order of desorption, that's 0 order, 1st order, 2nd order, and what we measure is d theta dt, which is the rate of desorption. Okay, so now Carl gives me a piece of anorthite, and so I do a TPD spectra of it, but before I do that, I put it in the chamber, I have it at room temperature, and I basically let it sit there. And then I come in and I do a TPD measurement, and I look at the measurement of M over Z, the 18 water signal coming off as a function of temperature, and I see very little chemisorbed water on the as-received sample. I see a big peak that sort of comes up around 400, and then it goes down around 750. This is molecular water. And so there's very little chemisorbed water here, but there's a lot of water that's being evolved from this particular sample. So then I do what is called a controlled dosing and pretreatment strategy. I park the sample and I move the temperature up to 550, where I'm sort of on the rising edge of this very big peak, okay? And then I come in and I purposefully dose water at a couple of Langmuirs, 2 Langmuirs, very small amount of water. And then what do I see? Well, I see this little peak here at 150, which is water clusters, which is like ice, it says ice. And then this big broad peak, that's chemisorbed water. And then there it climbs up again, but it goes to 0 at 400. So there's no chemisorbed water a little bit above, like, say, 375. That's important. That's the sort of maximum temperature that chemisorbed water is going to stick on this sample and essentially every other sample that we've looked at. Then it comes up. Okay, if I heat it at 750, it doesn't come up. It behaves the same. I get a little water cluster here, chemisorbed water, nothing else happens. So what's happening at this big spike here? So to the left, below 400 is chemisorbed water. To the right of 400 and higher temperatures is going to be water formation by this recombinative desorption channel. And that turns on somewhere around 375. Okay, I want to show this. So Michael Poston was a graduate student in my group, and he did a very good job on doing some of the first measurements of water chemisorption on a number of lunar samples. He used this apparatus, and he ran the samples, and he didn't have a lot of material. So he had to run a blank every time he ran a sample, and we do that all the time. But the blank had considerable data, a signal. So he had to take the sample signature and subtract the blank, and then he get the result of what the TPD from the overall channel is. And then he gets about 400 Kelvin. And this goes all the way out here, and if you analyze this, it turns out that's not enough. There's no real water sticking there. We redid this, and we found out that the limit for this is actually 0.9 EV. All right, so this just shows you that, and just pay attention to that. The limit to this is 0.9 EV. Grant showed this here. This is the recombinative desorption of water, and this is coverage dependent. And at low coverage, you get a low activation energy. At high coverage, it costs you more. But he also pointed out that if I put something in there, which is aluminum or magnesium or calcium or iron, I can move this binding energy down quite a bit. So not only is this recombinative desorption activation energy coverage dependent, but it depends critically on what the chemical composition of these minerals are, and in particular, the presence of magnesium matters. So then he showed you this, and this is the formation of water. There is no water added to the system. It's the formation of water by heating up an Apollo sample. And you can get water that's coming off right where I showed you where the recombinative desorption steps are. And Brant was very clear that it's just the leading edge of this blue curve that matters. And that's the area that we extracted out the activation energy that he used in his model. So what is this? We did an isotope exchange. We held this in vacuum, and this is the evolution of D2O. And you can see this is complicated. There's three features here. There's something right at the surface, something a little bit deeper in, and then there's this high temperature feature here. So we went and we did this, and so Brant already said this, so I'm not going to reiterate it. The appropriate way to analyze this is with this coverage-dependent activation energy expression that came largely out of Bruce Kay's lab. Bruce Kay is one of the premier experts in TPD, and so this is in fact the correct way to analyze this, and that gives us a number that's useful. This is what I want to show you, which is exciting and new data that we have fairly recently, is we went and we looked at the recombinative desorption yields from a number of Mare and Highland samples. And this is the D2O coming off, and I sort of showed you this already, but now I went and I did it with a Highland sample, and it is not the same. So the threshold for producing water is similar, so the recombinative desorption threshold is correct, but there are different peaks there. One thing to note, and I didn't point it out, but when I showed you the TPD of the Mare and Highland samples with the corrected background, there's a lot more water on the Highlands always. It's roughly a factor of between 6 and 10 more water coming from the Highlands, both in the chemisorb state and also in the released state. And then I didn't say a lot about this, but in the recombinative desorption channel, you can get H2. And so we went and we looked for H2 evolution as we heated this up to see if there was a correlation with that. And there is not a correlation with it happening at low temperature where the recombinative desorption channels are. But what we do find, and this is very reproducible, there's a significant amount of hydrogen that's produced as I get to higher temperatures. And we go through this and we can calculate the number density, and this is about 100 ppm. And this, we believe, is a pretty good measurement of the hydrogen that's in the sample, which is due to the original proton implantation events. But that takes a lot of heating to get these to come out. And so the deep hydrogen that's implanted far in, we can get it to be released, but you got to go to about 1,000 degrees Kelvin to get it to go. When you look at the background signal, it's only about 500. This is 45,000. So these are sponges for hydrogen. These are the lunar regulates, and I've never seen hydrogen released from anything at this rate ever. They're loaded with hydrogen. And then I'll stop and give you my conclusions, all of which I've already stated, is we want to keep the binding energies sort of within a bracket below 1 eV. The average is about 0.6, 0.7. You can get activation energies around 0.8. For making water, magnesium is the big key here. And high temperature release allows us to measure the amount of implanted solar protons in lunar samples. And that, I'll stop. Thank you.
We'll take a few questions. No questions? Bill?
Yeah, just a quick question, Tom. The emission of H2 is really neat. I'm just wondering, on the moon, we see an H2 exosphere that's actually relatively cool and, generated around 400K. And I'm wondering if, because it's undergoing a source right dynamically at that time, and re-emission, you tend to, get more hydrogens down at lower temperature. Whereas, actually cooking them and getting the hydrogens out is pretty cool. It's pretty cool, but if you had the source on at the same time, whether you get that H2 out at lower temperatures.
All right, so we can get some out at lower temperatures. It's just not that much. The relative percentage is low. And you can see it in this plot here. So you see this coming out at the 400, 500 area region, which is correlated where we know where there's recombinative desorption. So there is a channel there, but the the overall relative contribution is low. Most of the hydrogen in our measurements or in most beam measurements comes out at even much lower temperatures. It's really hard to keep hydrogen there. And so in this case, you know, this hydrogen that's being formed, it's being formed as H atoms that recombine and come up, but somehow there's a significant, and I do not know what it is, a significant amount of deeply, strongly bound hydrogen atoms that are implanted further within. It could also be that they're further in, and then they have a, you know, longer transport pathway to get out. And this is sort of probably part of this tail over here. But yeah, the amount of hydrogen that comes off at low temperature is very, very small relative to the total. Nor,
So how much water can you produce on Mercury?
well, okay, so I love that question because, and Brant might be able to give you that answer pretty soon. So we're running these simulations now with Mercury. Our position on this, though we haven't run the code, is that it will be significant. And the reason why it'll be significant is you're always above the temperature where you can get the reaction to occur. And there's a significant amount of minerals that contain magnesium. And so when you combine these two things together, the amount of water that would be produced, superficial water that would be produced by this process on Mercury should be substantial. We also think that there will be bands within Mercury in the latitude where there's a sort of a sweet spot in temperature and flux where you'll have enhancements, right? And so we're looking at that. If anybody can help us with this, one of the problems is we have what the fluxes are of the radiation and the proton fluxes.
Tom, comment. I'm trying to understand why the more data we have on the water exosphere on the moon, it seems to keep pushing that number down. So if recombinative desorption is occurring at these lower temperatures, what's happening to the water in the exosphere? I mean,
Okay, so Brant didn't specifically say this, but I don't mean to jump around like this. So right in this model, in his model, or in our model, this does not contribute significantly to the exosphere. That there is a source term, it either is photodissociated or it reabsorbs and redissociates, and this is actually part of the reason why you have it creeping up, right? So the solar wind implantation followed by heating is not a source term, right? Now I want to, if I can get to this, I want to make a point of this to connect with something Tony said, okay? Where we think there probably is a significant source of water that could end up in the exosphere is not by this recombinative desorption process, which is driven by a thermal cycle, which is the normal lunation, but it is due to impact events. And if I have an impact event, every bit of that water will be produced because I have a delta T spike, which is over 1,000. And so that's the source term. And we can integrate this and actually get a number as to how much water you can produce due to an impact event where I have a delta T spike of this amount over some volume element. And the other thing, and I was talking to Tony about this, we're absolutely sure that this water is not happy, okay? Because it's formed in a very non-equilibrium way. And so it's got a lot of vibrational energy, it's got a lot of rotational energy, and so it's going to behave differently, particularly from a photochemistry standpoint, than normal gas phase water. So this is a source term, and what is the fate of this is sort of an open question. I think it produces a significant amount of the OH that Tony sees, or that the observational programs are seeing, right? And that's an interesting, I think this is a good source term, and that's an impact event.
Any other questions? Let's thank all